In this short video, I want to talk about the distinction between the partial and total derivatives. And we're going to do this by way of an example, and we're going to take the temperature field as an example. So temperature, in general, is going to be a function of space, and it'll change with time also, t. And now, as a first example, we want to see how temperature changes. We want to take the derivative of the temperature. We are going to imagine that there's an observer, a tower, with the thermometer. And the position of the observer is fixed, so the observer is not moving around. And there's some air that's generally colder in this direction, and warm in the other direction. And then the air is flowing in this direction. So the wind is blowing in this direction, and the warm air is moving past the observer. And the observer, even though he's not changing, his position, R, will be fixed, but the temperature will be changing as a function of time. So what the rate of change of temperature that this observer will observe is the partial derivative of the temperature with respect to time, and that will just be the limit as delta t goes to 0 of t of r t plus delta t minus t of r t divided by delta t. Now, because r is fixed, the only thing that matters is the change of time, temperature with time, and so that's the partial derivative, the derivative of t holding r fixed. So that's the first example. Now, in the second example, we're still going to have generally warm air over here and cold air in this direction, but this time the observer will be moving. So we're going to have some blimp moving at a speed v, and on this blimp there will be a basket with an observer. Now this time I've got to tie the basket to the balloon, otherwise she's going to fall and she won't be so happy. So let's imagine in the first case that the air is still, but there's a temperature gradient from cold to warm in the atmosphere, and as she's flying through the atmosphere, she's going to also measure a rate of change of temperature, even though the temperature is not changing with time. It's going to be because her position is changing and she's moving from a region of cold to warm air. So in that case, the derivative dt of r is going to be analogous to the way we did the derivative of the potential energy when we derived Newton's law. It will be equal to the limit as delta t goes to 0 of t at r So this time temperature is changing implicitly because the position r is a function changing with time. And we can rewrite it this way. This is the change in the value of the function. That's going to be equal to the limit as delta t goes to 0 of delta r dotted with the gradient of temperature. That's the difference in the temperature, m divided by delta t. And now we can use the fact that if r is the position of the thermometer, we have delta r is r at t plus delta t minus r at t. And if I divide through by delta t, and I take the limit both sides, then what I get is just the velocity, right? That's the definition of this velocity v. And so this becomes just v dotted with grad t. Now in general, the temperature will change for two reasons. One, because it's changing with time explicitly, and the other one because the position is changing. And so if we want the total derivative, we need to include both. So in that case, dt will be the limit as delta t goes to 0 of t of r at t plus delta t plus delta t. So this will be the general case where both the position is changing and the temperature itself is changing even when R is held fixed. And so this will be the limit as delta t goes to 0 . And here I've just expanded the temperature in its Taylor series, expanded in terms of the second argument, the time argument. So this is the Taylor expansion of t to first order about the point r at t plus delta t and t. And all this then is divided by delta t. And this will become, this minus this is what we've already called v dot delta t. So this will be v dotted with grad t. Sorry, not v dot delta t, v dot grad t. Plus, and here the delta t's will just cancel, dt, dt. And so this is the total derivative. Now there's a special case where the velocity v is the velocity of the fluid, of either the air or the water. And in that case, so v is the velocity of the fluid, so it's the material velocity. Then we call dt, dt. Sometimes we'll also write it capital D, t, dt, which is going to be partial t plus v grad t, where this is the velocity of the fluid material. Then we call this the material derivative, or sometimes it'll be referred to as the substantial derivatives for the derivative with respect to the substance. So this is the material. Or sometimes called the substantial. But the formula is true for any velocity, for any point moving with time. This will be correct. But in the special case where this v is the fluid of the material, then we call this the substantial derivative. All right, so that concludes this video.